Okay, buckle in. This is the tough one. Circular motion. Why people find this hard is, well, I'll explain why people find it hard. Because it is hard. That's why. Moving on. Something that moves in a circle at any point, as it moves in that circular path, the velocity is always at 90 degrees to the acceleration. As the acceleration is in the direction of the force, the velocity is also at 90 degrees to the force. Because its velocity is at 90 degrees to the force, that's why it moves in a circle. And that's the basis of all circular motion. The velocity is going in one direction at 90 degrees to it towards the centre of the rotation. That's the direction of the force. And that defines circular motion. So, centripetal force is the force on an object towards the centre of motion when it's exhibiting circular motion. Now, then we have lots of formulas which we don't have to learn. There's no need to learn any of these formulas. There we are. That's angular velocity. It's just the angle swept out at any time. Whereas ordinary velocity is distance, or distance gone in a certain direction in time. Angular velocity is angle in radians per time. And you just divide the angle that you swept out in however many seconds by the number of seconds. Here, for instance, we have a complete circuit. And when you go round once, you've gone through an angle of 2 pi radians. So whenever you have the period of the oscillation, i.e. it's gone round in 4 seconds, capital T usually used for period, then 4 seconds, 2 pi radians, that's the calculation up there. 2 pi divided by 4 gives you pi over 2, and the correct units are radians per second. You can extend this into other formula. Here are the next formula you need to do. This formula is for the linear velocity and its relationship to the angular velocity. You timed by the radius. You don't remember it. Why don't you remember it? Think about it, think about it. Why don't you remember it? Because it's in the little book, isn't it? So if we already know the angular velocity and we already know the radius, it's written somewhere, there you are, 6 meters. We simply multiply the radius by the angular velocity and we get the ordinary velocity, which is in the old-fashioned meter per second we're already used to. We can then move on and also do acceleration as well. Acceleration, yet another formula. We times r by omega squared this time. So we're adding another omega essentially. Omega is pi over 2, so we square that, multiply it by the radius again at 6, and it comes out again as a linear acceleration in meters per second squared, this time as 14.8. These are just plug and play formulas. There's the formula, plug in the number, press play on your calculator. They are not complicated sums. And of course, because it's an acceleration and because centripetal force exists, you simply multiply this acceleration by the mass of the object and you get the force towards the centre. Now, this can be manifested as the tension in a string as you put a weight on a piece of string and wind it around the top of your head. Like, you know, when you have a buzzer, when I was trying to illustrate Doppler by putting the rape alarm on the piece of string and winding it around my head, and you heard the Doppler effect going off. The tension in the string is its acceleration times the mass of the rape alarm, because that's the force out. And the reason it travels in a circle is because the two are balanced. The tension balances the centripetal force. And anytime we go around a corner, whether you're in a car or on a camel, you experience, oh hello Eric, you experience this centripetal force. So we go back to the weight on the piece of string. Well, string or rope? I'm going to go with string. Weight on the end of a piece of string. Strong string if it's got 10 kilos. String. As we said, the tension is 98 newtons. The force up, force down must be balanced. But if we swing this thing, and you know, who doesn't like a good swing, the actual tension increases by the centripetal force, which we've calculated over here. I just have to change the colour. There you go. That's it. That's the formula for the centripetal. Now you might say that's not the same one we had earlier, but it is equivalent. All we've done is substituted V for where omega was, and we've ended up with V squared over R instead of omega squared R. But you can do it with either formula. You put in the numbers, you get an extra force of 26.7 newtons, which you add to the 98 and end up with 124.7 newtons. You have added to the tension in the string by rotating it, just like you added to it by jerking it upwards when you were lifting it. Now, so if centripetal force is equal to mv squared over r when something's rotating, if you actually have a satellite, then the gravitational effect will balance the centripetal force. That's what's happening in a satellite. The gravity, given earlier from gravity's law, F equals gmm over r squared, that balances it against the centripetal force, mv squared over r. And because they're balanced, we can equate them, something physicists love to do. And after we've equated them, we can use them to work out a new formula we didn't have before. And here it is. That's equated it at the top. And then we cancel the mass of the satellite, i.e. what's on the end of the piece of string, or what's the satellite going around the Earth. That cancels. We convert the V to distance over time. Well, in a circle, the distance is its circumference. And the circumference of a circle is 2 pi r. Now, we use d here out of tradition for the formula when it was originally used. D being the distance between the satellite and the centre of the Earth, and not the radius of the Earth. And it's not really the radius of the orbit either. It's a little bit more complicated, but it's the distance from the centre of the planet, the Earth in our case, to the actual satellite itself, not to the surface. And time is just the period, the time it takes to go around. We still have the left-hand side pretty much the same. All we do is rearrange all these figures and we get this rather grand formula at the bottom, which, of course, you don't have to remember. It is also in the logbook, which relates the period of a time a satellite takes only to the distance it is out. As long as the planet, which is the big M, is constant, if that was, for instance, the mass of the Earth there, then the mass of the Earth doesn't change. So the time a satellite takes to go around is only dependent on how far it is from the centre of the planet it's orbiting. And that's how we can get a geostationary orbit. A geostationary orbit is exactly the right height that it orbits once every 24 hours, the same as the Earth goes round. So the satellite appears to stay above the same point on the Earth's surface constantly. This is because its orbit and its period and the period of the Earth's rotation are the same. So a geostationary 24-hour orbit period. It's a very long way away. Compared with the space station, it's several thousand times further out. I wrote this out again in the hope that this would be any help. I looked at the other proof, and it's all a bit like red and thing. This is a much more classic, and you can freeze and go through this if this is any help. Remember, on the left, at the very top, that is the force of gravity. And this is the centripetal force, and we equate them. And we're just going down, doing exactly what I said before, cancelling the different figures that we can. For instance, here we cancel the square of the d with d, and we cancel the two little m's, the mass of the satellite, and we end up with the lower figure here, which we then convert v squared, etc., and rearrange. This is a little example I did, mainly to increase the height. Now, many of these questions ask for the height above the surface instead of the actual distance from the centre of the planet. So you do the calculation, you have the formula, which you lift from the logbook. There it is in orange. You put all the numbers in and you end up with a d, which is 1 times 10 to the 10 metres. That's the distance from the centre of the planet. There's nothing really complicated. You look up the universal gravitational constant, you look up the mass of the planet. Of course, you have to convert your time into seconds. That's true in all physics. You can't use hours and days for anything. You have to use seconds for everything in physics. But the final stage, which I've done here in a dark blue, you'll see how I work out the height above the planet. I've simply subtracted the radius of the planet to get the height above the planet's surface. This is something which quite commonly crops up as a last section. It's true that this is often quoted in the press, but as scientists, we would always use the distance from the centre for our calculations, so we wouldn't really quote the height above the surface. And finally, for all of mechanics, simple harmonic motion. What is simple and harmonic about motion? Well, simple harmonic motion is where we say A is proportional to S. What it means is that the acceleration is proportional to the displacement from the centre of an oscillation. So the further you get away from the centre, your rest point, your normal place would be if it wasn't moving, that centre of oscillation, the further you get away, the more acceleration you have. Not the more velocity, the more acceleration, so the more force. Remember, acceleration and force are proportional to each other. So, in the logbook, it's often written in a different form, but that's the way we need to remember it. The omega squared is important, very important in calculations, as we'll see later, but it's basically a constant which turns the proportionality into an equation, something we've been talking about a lot in this section. Hooke's law is an example of simple harmonic motion because Hooke's law, which is one of the oldest laws, as I may have said, is force is proportional to displacement. Well, force can also be written as mass times acceleration. So if the mass is held constant, which it is, it's not changing on the end of the spring, then we can also write acceleration is proportional to S, which is just rewriting simple harmonic motion. So if you have a spring with a weight on it and you pull it down, then as you release it, it is exhibiting simple harmonic motion. This is also true of a simple pendulum or something bobbing up and down in the water. These are all examples of simple harmonic motion. Now, calculations of these, a little bit more, I've said they're easy, but really is it? Basically, again, if we write down the whole of Hooke's law, F equals Ks, K being the spring constant, we can rewrite it as A equals K over M S. Now that's in exactly the same form as A equals omega squared S for simple harmonic motion. So the constant omega squared must be the same as the constant K over M. They're actually equal to each other, and we can use this fact in many calculations. So it's definitely worth remembering if you're going to do this section, particularly if you're going to attempt it question 6 or the mechanics question of section 12, which is usually 12A. So the last thing, pendulum. You have to go to my YouTube channel and look at how I did the pendulum. I'm not particularly proud of it, but it is funny. This is the pendulum as it should be drawn. I would definitely advise against drawing the way I did it on the exam paper. I do think people would find it a bit strange, especially if they've never seen my video, which, you know, given the number of views I've had so far, is very likely. This is the length of the pendulum to the centre of the pendulum bob, if you notice, because the centre of gravity of the entire pendulum is the centre of the pendulum bob, because it's very heavy. There's a great weight or mass compared with the string. We also have a split cork. The split cork, the idea is that the point of oscillation is constant and doesn't change as the thing oscillates, and we have a timer. And sometimes we measure the string with a ruler, and we use the vernier calipers to measure the pendulum bob. And if you're asked for a complicated way of measuring the length, that would be the way to do it, to measure the pendulum bob with the vernier calipers and divide by 2. But the pendulum bob will experience simple harmonic motion if it goes to a small angle. It must be less than 5 degrees. That's actually quite important. If it's greater than 5 degrees, it doesn't really exhibit simple harmonic motion. Now, this is the calculation I was talking about. This is where I left it, t squared against L with a straight line. Now, if t squared is on the y-axis, that is equivalent to y. And if L is on the x-axis, that is equivalent to x. Meaning that everything else is m. There's no c. C is equal to 0. So everything else in that equation, which is not mentioned or plotted onto the graph, must be the slope. So the slope is equal to, as you can see, 4 pi squared over g. So by manipulation, by moving the g, making it the subject of the equation, we can see that little g is 4 pi squared divided by the slope. This is how we work out and use the slope in every single equation in physics. The slope is what's left in the equation when we've put the y and the x out. It's the extra piece, the constants, the fixed points, the things we are not changing during the experiment. We are not doing the experiment on. That is what we can use. Okay, I've got 2 questions for you. This one, a fairly simple one. Some preambles, relationships, the derivation, a little bit of chat, and then it asks you for the height of the GPF above the Earth's surface. So it's exactly the question I had earlier. Put in all the figures, work out, and then subtract the radius of the Earth. Then the speed of the satellite. Well, that's an absolute doozy. The speed of the satellite here, the velocity, is 2 pi r, the circumference, over the period t. Nice, easy question. Time it takes a GPS signal to travel. Well, time from Dad's silly triangle, time is the distance over the speed. Okay, so the distance is the height above the Earth's surface, not the radius, but the height above the Earth's surface. And the speed, 3 times 10 to the 8, is of course the speed of light. And then there's a bit about radio waves. What type of radiation is lowest? Next to radio waves, well, it's probably microwaves, isn't it? Micro. So you can probably write infrared as well. This question, much better. Very nice little question about kinetic energy as well. Also features this gentleman, one of the really, really forgotten heroes of Irish sport, Petal Callaghan from Kanturk, an enormous man who threw the hammer, won 2 Olympic gold medals. Why there aren't statues of this guy everywhere in the country, I have absolutely no idea. I don't know, maybe he voted for the wrong party. Absolutely no idea. Well, good luck with all of that, and I hope this was some help with you for those people who are considering answering questions on mechanics. To which my reply, don't!